that's where we will kind of bring this discussion between algebra and geometry to an end. Okay, and what we will do next will be we will formalize our intuitive understanding of constraint optimization in the first theorem of constraint optimization. We're going to put together all our intuition into something more formal. It is like the bedrock of constraint optimization. Many of you would have heard the word also for this theorem, or the name for this theorem. They're called KKT conditions, Karush-Kuhn-Tucker conditions, right? So I'm sure you've come across this name in many papers. So let's take a dig at this. Okay. So end. Okay. Right. So they are called the first order necessary conditions, and because this is a particularly long phrase to write, we will just use the short form FONC. Okay. Also called as, after the people who discovered it, Karush. So in fact, in the literature, you will find most people just call them KKT conditions. Almost no one will say FONC. Okay. So to start our discussion of constraint optimization, the tool that we have discovered is the Lagrangian, right? So the Lagrangian is going to be as before. Lagrangian is a function of x and lambda, simply written as fx minus, okay, and I belongs to, it includes both equalities and inequalities. Okay, so it's a relatively long sequence of statements that we have to write to put this KKT theorem on paper. Okay, so let's do that with this Lagrangian in mind. So the theorem has a if, bunch of things have to be true, then these things follow. So we'll write it as if and then. So what are the if parts? Okay, so this is first order necessary conditions for what? No, for constraint optimization, but for what? To check whether or not x star is a stationary point. Okay, that's what this is a test for. This is not an algorithm. This is a test that if you give me a point x, I will subject it to this test and tell you whether or not it satisfies. Okay, so that's the first part. If x star is a local solution to let's write it like this, to minimize of x belonging to this thing f of x. Obviously, this is what I want. The second is reasonable condition to apply, because we want to do calculus. If you want to do calculus, what should we assume on f and c's? Differentiability is to be expected, right? So f and ci's are continuously differentiable. Okay. What is the third condition you think? It's something very related to what we just did. Louder. LICQ, right? LICQ holds at x star. Okay. So if you give me all of these three conditions, then comes the then part of the theorem. Okay. Then there is a set of Lagrange multipliers lambda I star, right? So then there is a set of Lagrange multipliers. Okay, they are such that the following are satisfied at the optimal point. So what are these things that are satisfied? This is what we have already studied. We're just going to formalize this. What is the first condition in constraint optimization? Gradient of what should be 0? Lagrangian. That's the first condition. Gradient of the Lagrangian with respect to x at the optimum point should be 0. Okay. What is the other thing? The next two steps are very, very obvious. We should be on the feasible set. That means equalities should be satisfied. So Ci of x should be equal to 0, x star, let us say, okay, I belonging to equality set. What should be point C? No, look, it's just a analog of point B. What would it be? Inequalities, right? So Ci of x star should be greater than equal to 0, I belonging to inequality. Okay. So I can tell you this point is not complementarity. What do you think it should be? There was a small, if you recall the example between equality constraint, inequality constraint, there was something different between the two. What was that in relation to the Lagrange multipliers? They were positive. The Lagrange multipliers were forced to be positive, in which case? Inequality constraint. Was there any such constraint on the equality case? No, right? So that point comes over here. So lambda I should be greater than equal to 0 for I belonging to the inequality set. Okay. And finally comes our complementarity condition. Lambda I Ci equal to 0 for all the, right. So you have these A, B, C, D, E conditions which will hold if these 1, 2, 3 are satisfied. Okay. There is one final piece to this which talks about the uniqueness of lambda star. Lambda star, remember lambda star also has to have an optimum choice, right? So there can be many points, let's just note that over here, there can be many points where A through E hold, okay, but if you give me LICQ, which is 0.3 over here, then the lambda star is also unique, okay. So but if 3 holds, lambda star is unique. Okay. So these are in very, very brief, these are your famous KKT conditions, right? To satisfy them, there's not a very stringent condition. What do you have to make sure? The objective function and constraints are differentiable, continuously differentiable. You need to check LICQ, right? To check LICQ, what do I have to do? Do I need to do feasible sequences? No. What do I have to do? Look at all the active gradients, put them together in a set, figure out whether or not they are linearly independent. I can check that. So if all of these 3 criteria are satisfied, right, then this theorem applies, and only then this theorem applies. Then there will be a set of Lagrange multipliers lambda. They may not be easy to calculate, that's a different matter, but all of this will hold true. Gradient of Lagrangian is 0, right, you are on the feasible set, that's point B and C, and the complementarity condition holds. Okay. So I have not yet written a proof over here. In the examples that we did, equality constraint, inequality constraint, also I didn't give a proof, right? So we can't run away from giving a proof for too long. So I will give you a proof of this by means of an example. Okay. So let's see how much. Actually, we are running short on time. Okay, so let me start out with the statement, and we won't do the proof. We'll start out with the statement, and we'll take an example. Our favorite example is what we're going to take, right? So this is not a full proof. Let's call this a proof sketch. Okay, And for that our example was f of x was equal to x1 plus x2, and the constraint was, I'm going to take two constraints, to interior of the circle and right. So we did this example once before. This was two inequality constraints. This is that example, right? So right, I am here. What is the feasible set? Upper disk, right? Upper disk is my feasible set. Okay. And so what we want to check, if I give you some candidate point, so first order necessary conditions for x star to be a local minima. This is what we want to check. Okay, so we will apply it to this, and that will help us to formulate the proof. Okay, so C, oops, this is C1. Obviously, at this point x star, the inequalities must be respected. Okay. The second part is, see here the trick or the difficulty with inequalities is that they may be active, they may be inactive, and I have two of them. So how many possibilities are there? Actually, four possibilities. They could, right, depending on greater than or equal to, there are four possibilities. So we'll have to check for all of these four possibilities and then see depending on the point, right? So let's note those down. Okay, so if C1 of x star is equal to 0, I haven't specified yet, I'm leaving it general. If both of these guys are 0, right, then what all should happen? So the constraints are active, right? What does that say about the Lagrange multipliers? They have to be greater than 0 because it's an inequality, right? So C1x equal to 0, C2x equal to 0, does that say grad C1 equal to 0? No, obviously not. So the gradient of the Lagrangian will give me what? Grad f x star minus lambda 1 grad C1 minus lambda 2 grad C2, this should be equal to 0. This should happen. Lambda 1 greater than equal to 0, lambda 2 greater than equal to 0. This is the first possibility. This should happen. I have to verify whether or not this happens. Yeah, I mean, you can, I'm not assuming it. Look at the f and c. Are they continuously differentiable? Yes. And let's say I'm taking my candidate point x star and I'm going to investigate. Now, without specifying which point I am going to take, I'm listing out all the investigations I have to do. For, yeah, exactly. LICQ we will verify. We will verify. Okay. Actually, with the constraints which you have taken, you can see LICQ will be satisfied because there are no funny whole square terms happening there. So LICQ will also be satisfied. So the then parts of the theorem gives me this, right? What if I had case B where C1 x star is strictly greater than 0, C2 x star is equal to 0? Then what should I have to verify? If C2 x star equal to 0, gradient of Lagrangian has to be 0 anyways, right? So, but if C1 x star is strictly greater than 0, what does that say about lambda 1? What should happen? Lambda 1 should be 0. So, the gradient of the Lagrangian will give me what? Grad f x star minus what? Only lambda 2 grad C2 x star is equal to 0. Okay. And is there any condition on lambda 2? Lambda 2 should be greater than equal to 0. Okay. So this is, I'm giving you practice in inferring what does this, how to use this theorem. What are the various conditions that this theorem tells me to check for? Okay, so that's why I'm going step by step over here. Condition C is the symmetric one. C1 x star equal to 0. C2 x star is greater than equal to 0. Then what all happens? Which of the lambdas will go to 0? Lambda 2 goes to 0 because of complementarity, right? So lambda 2 equal to 0. Gradient of the Lagrangian has to be 0. So this will simply be grad fx star minus lambda 1 grad c1 x star equal to 0 and lambda 1 greater than equal to 0. This is what the theorem statement says. And last not the least, what would it be? Both the inequalities are inactive. So I have C1 x star greater than 0, C2 x star greater than 0. Okay. What happens to my Lagrange multipliers? Both have to be 0. Lambda 1 equal to 0, lambda 2 equal to 0. Gradient of Lagrangian will simply become grad f. Grad f star equal to 0. Anything else? No, right? So that's it. So so from here on I have to prove these statements, right? What I've merely done is I've taken the theorem, applied it to this problem and figured out what are all the possibilities that will happen. If my x star happens to be on the boundary of one constraint, not on the boundary of one constraint, not on the boundary of any constraint, whatever, these 4 possible combinations are there. This is what the theorem tells me. So I have to go in and painstakingly prove each one of these to be true, and prove this to be true in a way that is not dependent on this problem that I've taken, but in general. Okay, so that's what I'm going to do in the next session. So this is just to tell you what to expect. Huh. You would have a lambda 3. If you had a third constraint inequality, you would have a lambda 3 as well. You said it's an equality or inequality? Equality. So it will always be equal to 0. I mean, it's always C3x is always equal to 0. So you would have to maintain that. Lambda 3 need not be greater than equal to 0. It can be anything, because the greater than equal to 0 condition is for inequality. For equality, it can be anything. For, yeah, I mean, if it is, if it is inactive, then it has to be 0. That intuition we got from the example that we took, right? We saw that in the case where I had either parallel or anti-parallel configuration. In one case I had no feasible direction, in one case I had a feasible direction. So I was interested only in the one where there was no further direction to go to, and for that I needed parallel, and parallel made it such that lambda was positive. So that is because you define the inequality as 2 minus x1 square minus x2 square. Correct. Exterior, okay, very good. So maybe that's what we can end this discussion with. So we have been talking about, for example, single inequality constraint was interior of the circle, f of x is equal to x1 plus x2, and I want the minima of this. Now he is flipping the inequality, he is saying x1 square plus x2 square minus 2 greater than equal to 0. So so this is really important. Before you begin to solve the problem, you should ask yourself, is this a sensible problem to solve? Is it? It's not, because this objective function now is not bounded from below. The minimum you can achieve is minus infinity, right? So don't even attempt to solve it, right? It's like saying what is minimum of log x, right? So it's going to blow up. So check that before you start solving a problem. After doing all of the hard work, you realize you have that oops moment that I needn't have bothered. Okay. Intuitively, okay. So how did I get the tangent cone to be? further back. Yeah, yeah, this one. So when I took the sequence zk, I got a vector that is pointing in the +1 direction. I mean, along the y-axis. When I took the sequence wk, the vector is pointing in the -y direction. The directions are +y or -y. So I could have in the first cut written it as 0, ±1. But then you notice that this tk is in my hand. It only needs to satisfy the property that for large values of k it tends to 0. So with tk, if tk is defined like this, the norm of the vector, then I get ±1. Supposing tk was defined as 2 times the norm of the vector, what is the vector that I get? Tangent vector? Half, ±half. So it's entirely in my hand. So like this, you can keep choosing different multipliers over here, different tks. I will be able to get the entire. So that's why I'm writing it as 0, d2. d2 belongs to real numbers. Hmm. Yeah, you can take, yeah. So a sequence is not uniquely defined. There are infinite possible sequences. So this is left to you. That's why I kind of cheated by taking a easy case, right? If I choose C1x equal to 0, I'm on the boundary of the circle. It's relatively easy for me to define this feasible sequence. Now, if you say that I live inside the circle, then I have a lot more freedom and creativity to define any kind of crazy sequence that gets me. So it's, you have to define it. The trouble is yours. Okay, but it can be done. Correct. So you want the proof. So the intuition part is clear to you. So okay. As far as intuition goes, it's clear to you why it only holds true for the active inequalities. For equality, there was no reason or need to constrain in that way, right? That you got from geometry, that you're convinced. The proof part is what we will do in the next session. That why is it forced to be positive or in a way that's that's a good way of looking at it. Yeah. Whether I write the constraint as C1x equal to 0 or minus C1x equal to 0, it doesn't matter. So by flipping C1 to minus C1, grad C1 also flips a sign, so it doesn't really matter. It matters because you change the half space from here to there.